Hi, my name is Kaesi Manakkal. I'm a second-year PhD student from University of Texas, Arlington, and my research lies in systems and security. My collaborators include Nathan Daughety and Marcus Pendleton from Air Force Research Lab, and Dr. Hui Liu from University of Texas, Arlington. Today, I want to talk about the microkernel versus the monolithic kernel. The kernel is a core component of an operating system. It manages system resources and acts as a bridge between applications and the underlying hardware. This slide presents a textbook classification of kernel architectures. On the left, we see the monolithic kernel design. In this model, most operating system services, such as device drivers, file systems, and memory management, are integrated into the kernel space. This creates a large, feature-rich kernel, which simplifies interactions for user programs and improves performance through direct internal calls. However, this design comes with a major trade-off. The large code base is harder to secure and maintain. A single bug in any of these components can potentially crash the entire system. On the right is the microkernel architecture. Here, only the essential services, like CPU scheduling, memory management, and inter-process communication, are kept in kernel space. All other components, including file systems, device drivers, are moved to user space. This results in a smaller and more secure kernel that can even be formally verified, as demonstrated by systems like SEL4. That said, microkernels are generally harder to work with. Since fewer features are provided by the kernel, developing and debugging user programs becomes more complex due to the increased reliance on message passing and system modularity. This talk focuses on applying microkernel concepts to secure applications running atop monolithic kernels, which remain the dominant model in cloud infrastructure and modern server environments. To begin, let's look at the modern application landscape. Today, most applications follow a microservices architecture. Instead of building one large monolithic application, developers split their application into many small interconnected components, each responsible for a specific function. These microservices communicate and work together to deliver the full application experience. This design offers several major benefits. First, it allows for horizontal scaling, where we can scale out individual components based on demand. It also provides flexibility in deployment, since services can be updated or replaced independently. And more importantly, it offers fault tolerance through redundancy, helping to ensure high availability even if some components fail. To deploy these microservices efficiently, containers are widely used. Containers are lightweight, start quickly, and are easy to provision on demand, making them a natural fit for dynamic scalable environments. While containers are popular for deploying microservices due to their low overhead, especially when compared to heavier mechanisms like virtual machines, they come with the trade-off: weaker isolation. The root of this problem lies in the large attack surface between each container and the host kernel. Unlike virtual machines, which emulate hardware and run their own kernels, containers share the same host kernel. This means that all containerized applications rely on that shared kernel to manage system resources. In practice, this exposes the kernel to a wide interface, over 400 system calls that a containerized process can potentially interact with. Each one of these system calls represents a possible entry point for an attacker. So, if there's a kernel vulnerability, say in how file systems are handled or how inter-process communication is handled, a malicious container could exploit it to break out of isolation, affecting other containers or even the host system. This issue highlights the isolation problem in container-based systems. While we gain performance and flexibility, we also expose ourselves to higher risk due to shared kernel dependencies. To address the security concerns we just discussed, the current solution in cloud environments is to run containers inside of virtual machines. This approach leverages a hypervisor like KVM to provide strong isolation, by separating clients at the virtual machine level. Each container runs inside of its own virtual machine, which includes a guest operating system and kernel, providing a dedicated environment for the tenant or service. This setup significantly reduces the risk of a container escape affecting the host system, because the kernel interface exposed to the container is no longer the host kernel. It's the guest kernel, and interactions with the host are limited to a much smaller set of hypercalls, as shown in the bottom of the diagram. While this offers secure isolation, it comes with a higher performance cost. Running an entire guest OS per container introduces high CPU usage, a large memory footprint, and increased I/O latency. In essence, we're trading security for efficiency. This is especially problematic in large-scale deployments, especially for microservices-based applications with hundreds or thousands of services per application. So while this method is widely adopted in the public cloud today, it motivates the search for new solutions that can achieve strong isolation without incurring such overhead. This chart visualizes the core trade-off between isolation and performance. On the x-axis, we have isolation, from strong on the left to weak on the right. On the y-axis, we have performance overhead, ranging from high at the bottom to low at the top. Traditional virtual machines provide strong isolation, but at the cost of high overhead. Some in-between approaches like micro-VMs or unikernels that reduce the cost slightly while still offering moderate isolation. On the other end, we have containers, which offer excellent performance, but expose the system to weaker isolation. So our question is, can we have both? That brings us to our proposed solution, LITESHIELD. As shown in the top left quadrant, we aim to provide the security of virtual machines with the speed and efficiency of containers. The key idea to our solution lies in its new Userspace microkernel architecture. Instead of running containers directly atop a shared kernel or within full virtual machines, we decouple the guest applications from their guest kernels. In LITESHIELD, the guest kernel is decomposed into a set of Userspace microkernel services. As shown in the figure, each application process interacts with Userspace microkernel services like networking and file systems through fast interprocess communication channels. This design keeps all interactions between applications and system services within Userspace, significantly reducing the reliance on the host kernel. Only a thin interface connects the Userspace microkernel services to the host kernel, typically involving just a few dozen system calls, compared to hundreds in traditional containers. This gives LITESHIELD a virtual machine-like isolation boundary, while avoiding the overhead of running a full guest operating system instance. All major kernel functions like networking, file access, and time management are handled entirely in Userspace. For performance-critical tasks, LITESHIELD supports direct access to underlying devices, enabled through Userspace libraries like DPDK and shared memory. Finally, this architecture is not only secure and efficient, but also modular and cloud-friendly. Microkernel services can be developed, extended, or replaced independently, making the system more maintainable and adaptable to modern workloads and hardware accelerators. So in short, LITESHIELD combines the security advantages of microkernels with the performance and agility of microservices, all built on top of our new Userspace microkernel architecture. The more we can accomplish in user space, the less we must do in kernel space. While LITESHIELD moves most kernel functionalities into the user space, it also raises a challenge we call non-deligible system calls. These are system calls that must be executed within the same address space as the application that made them. This includes memory management calls like mmap and process management operations like fork, clone, and exit. This is due to the implementation of the existing Linux kernel. These system calls can't simply be redirected to an external user space service, so how do we handle them without modifying the kernel? Our goal is not to introduce kernel changes, since we focus on compatibility with unmodified Linux. Our solution is to allow these non-deligible calls to run, but to trap and monitor them using ptrace. When a guest application issues a non-delegible system call, it's intercepted by LITESHIELD's core microkernel service, which performs sanity checks, validation, and other inspection before allowing the system call to proceed. This approach preserves system integrity while maintaining the thin user-to-host system call interface. In the diagram, you can see delegible system calls go through fast IPC and microkernel services, while non-delegible ones are carefully monitored on their path to the host kernel. This arbitration mechanism ensures correctness and adds a layer of defense and depth, keeping applications contained even when full delegation isn't possible. Another major challenge we face is handling user space kernel bypass solutions, particularly for high-performance networking and storage scenarios. In a complete kernel bypass model, each user space application directly accesses a physical device, for example, a network card, entirely bypassing the host kernel. While this offers excellent performance, it comes with a major limitation: no sharing. Every application would need its own dedicated hardware, which is not scalable and simply infeasible in cloud environments where resources must be efficiently shared by many tenants. To overcome this, we adopt a more practical partial kernel bypass approach. Instead of fully bypassing the kernel, we leverage emulated virtual devices, such as tap devices for the networking scenario, to act as virtual NICs. These tap devices work seamlessly with user space libraries like DPDK, allowing LITESHIELD to preserve the benefits of reduced kernel involvement for performance-critical operations like I/O processing while still supporting resource sharing. This design is intended to strike a balance, delivering high networking performance while remaining scalable. The final challenge we address is supporting legacy Linux applications. Rewriting these applications to work with the new system call interface would require significant engineering effort. To solve this, we used a technique based on LD preload. At runtime, we inject a custom library into the application's address space, leveraging the libsystemcallintercept library, which provides fine-grained system call interception through inline hooking and binary rewriting, allowing us to intercept system calls without changing the application binary. Intercepted system calls are then redirected to LITESHIELD's user space microkernel services via a fast IPC mechanism using shared memory buffers. This combined approach ensures compatibility with unmodified legacy applications while maintaining control and redirection at the system call level, making LITESHIELD practical for real-world deployment. Now let's look at our implementation. First, we use a shared memory-based IPC to replace traditional system calls. Guest applications are linked with the dynamically injected LD preload library that intercepts traditional system calls at runtime. Second, we implement a user space networking stack using fstack, which is built on top of DPDK. We've modified fstack's main loop to monitor LITESHIELD's IPC queue and process network requests in user space. Each fstack instance binds to a tap device, allowing multiple containers to share a physical NIC, a critical capability for scalability in cloud environments. Third, we built a user space file system service that emulates an X2-like storage stack. It's backed by a memory-mapped file, enabling efficient file operations without involving the host kernel for most tasks. This approach avoids kernel double caching and supports high-throughput I/O, particularly for workloads like Redis or FIO benchmarks, as we will show later in our evaluation. Together, these components allow LITESHIELD to serve most system calls in user space, reducing the user-to-host system call interface to just 22 calls, on par with hypervisor-based isolation, but without the heavyweight VM stack. LITESHIELD's core services, not including fstack, or the user space file system service, take up approximately 7,000 lines of code. For our test bed, we used a system with a 4th generation Intel Xeon processor and 96 gigabytes of DDR5 RAM. We used Docker containers, a KVM-based virtual machine, Firecracker, and gvisor as baselines for comparison. The first benchmark we ran is a system call latency test. We used the getPID call because it's very lightweight and allows us to measure the context switch overhead of a system call that does nothing. The read test was performed similarly by calling read on a file filled with zeros. This was chosen because it involves more kernel code paths, such as Linux's VFS. This is used to demonstrate the advantage of performing these actions in user space. As our solution is smaller, the path for such a call is shorter, reducing the latency. We also ran FIO to compare our solution against the baseline solutions. For the direct I/O test, we disregard gvisor and Firecracker as they don't provide a way to prevent caching. For the cached I/O test, our solution can efficiently cache all writes due to the lower system call latency. Therefore, we achieve slightly higher numbers. We also ran network benchmarks for UDP and TCP. Our TCP performance is lower as our network stack is not well optimized for TCP and lacks some features like GRO. However, in the UDP test, which it is well optimized for, we can see the advantage of the short user space I/O path. Finally, we ran the Yahoo Cloud Serving Benchmark, YCSB, on top of Redis database running on our solution. The added disk, network, and system call overhead for the virtual machine solutions contributes to their lack of performance. For Docker's case, the lack of performance is likely due to its complicated network stack. In summary, we present LITESHIELD, a secure container solution that allows running unmodified Linux applications. We provide strong isolation by reducing the host-to-guest interface by moving kernel services to the user space. We replace traditional system calls with fast IPC calls using a preload library, and we use lightweight kernel abstractions to allow sharing hardware resources. Our evaluation shows that it has comparable performance to the baseline and is generally faster than the virtual machine-based solutions. Thank you.